Hello everyone. Today we're going to continue our discussion on vector space. Yesterday we talked about two specific type of vector space. One of them is Rn, which we expected to be a vector space because after all, that's the first type of vectors that you learn. And then we talk about matrix space, where we realize that matrix space is actually also a vector space, simply because a matrix is just basically a vector, but just arranged differently. So it's essentially a matrix is the same as a vector space Rn. Instead of arranging all the number horizontally or vertically, we arrange them in some kind of rectangular array that form a matrix. So today we're going to talk about a few more vector spaces. The next one should be obvious to you that this one is also a vector space. Number 3 would be an infinite sequence. So what does it mean by that? So let's consider this. Consider the set of all infinite sequences. In the form of vector x equal to x1, x2, ... forever. So if you look at this, you should realize this is very similar to just Rn, except that we don't have a last element in our set, meaning that instead of having ... x sub n, we just ... forever. And if you think about that, it is correct. And as a matter of fact, it should follow that this would be a vector space, but to be fair, we're going to define the following. So here would be our set of objects, which will be vector x in the form of x1, x2, ... to x. I'm sorry. Remember, it's an infinite sequence. So just ... forever. Well, to define two operations. So what are the two operations that we're going to define? Well, same way. If I have two vectors, two infinite sequences, and I'm going to add them together, that just means I'm adding x1, x2, ... to y1, y2, ... and so the sum, the sum would just equal to x1 plus y1, x2 plus y2, ... forever. And as you can see, that definitely defines an infinite sequence. So closure is automatically satisfied. Next, if I have a scalar s multiplied by vector x, then what would that be? That would be s times x1, x2, ... forever. And so that just equal to sx1, sx2, ... forever. And as you can see, that's just the same thing as what we wrote before in number 1, except that we don't write the x sub n, which is the last element. And of course, we also have to define the 0 element. So what is my 0 in this case? Well, 0 will be our 0 vectors, which will be just 0, 0, ... forever. And in this case, you should be able to see that if I were to prove all the 10 properties that we want to define a vector space, you find out that you're basically rewriting the same exact proof you would do with number 1, except that in everything that you wrote for number 1, you would just take out x sub n from all of them, and then voila, all of a sudden you have the same exact proof. And that would basically tell me that this has to be a vector space. And as a matter of fact, it's interesting to note is that, as I say, it should follow from Rn that this is a vector space. As I say, because it would be simply mean that you write out the exact same proof for Rn, except you just don't write the x sub n element as the last element and just let it go ... forever. And this space has a name. This space is sometimes called R infinity to indicate that it is an infinite sequence. Okay? So that's simple. But now let's talk about something that you don't think of them as vector space, but if you do, you find out that it surprisingly makes things a lot easier for you to do. So what would be our next vector space? Well, our next vector space is this. Our next vector space is number 4, I believe. And that would be a polynomial space. So what is the polynomial space? As the name suggests, it's relating to polynomials. So let's say we do this. Let P sub n be the set of all polynomials. Oops. Of degree n or less with real coefficients, so we don't want any complex coefficients in the variable x. And I would like to show you that this actually would form a vector space just like all the other vector space that we talked about before. And if you recall what I told you yesterday, what we're going to basically try to do is to try to turn polynomials, something that you don't normally think about as a vector, into a vector. More importantly, into a vector in Rn, or something similar to Rn, so that we can actually just talk about it as vectors in Rn. So I'll show you how that is done. So remember, to define this vector space, I have to define the following things. I have to define first what are the objects. So I'm going to define all the objects to be following. So all objects within P sub n would look something like this. I'm going P of x will be equal to a sub 0 plus a sub 1x plus a sub 2x squared plus dot 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 plus a sub n x to n. And that would define an object in P sub n. So that would be a polynomial of n degrees or less. And if it's less than n degrees, then that would mean that a sub n could be 0, or some of the other one becomes 0, and and it make it into a lower degree. But it would be in this form. Just could be with some of the a sub 0 to a sub n being 0, then changes the degree of the polynomial. How do I define addition? So I'm going to define two basic operations on this set of objects. So let's define the following. Let's say I have P of x, which is a sub 0 plus a1x plus a2x squared plus dot 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 plus a n x n. And I'm going to define a second element in this in Pn. Let's say I'm going to call it Q of x, and that would be b sub 0 plus b1x plus b2x squared plus dot 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 plus bn x sub x to n. So suppose I have these two objects. Now what if I want to add them together? Let's say I want to add p of x plus q of x. Then what do I do? Well, basically I'm adding these two things. So I'm going to say that's the same thing as a sub 0 plus a1x plus a2x squared plus dot 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 plus a n x to n plus b sub 0 plus b1x plus b2x squared plus dot 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 plus b sub n x to n. Now how do I add these two things together? Well, notice that when we're adding polynomials together, what do we do is to combine like terms. And therefore, basically tell me that this come out to be a sub 0 plus b sub 0 plus a sub 1 plus b sub 1 x plus a sub 2 plus b sub 2 x squared plus dot 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 plus a sub n plus b sub n x to the n power. Now, hopefully some of you have a little deja vu based on the way we're written. And if you do have it, that's great, because you kind of slowly try to see what we try to do with vector spaces. And if not, don't worry, I'll point it out to you when we get to toward the end. Next, we're going to define a scalar multiplication of an element of vectors. So in this case, I'm going to say, what if I want to multiply s with one of the element p of x? What happened? Well, that just become s multiplied by a sub 0 plus a1x plus a2x squared plus dot 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 plus a n x to n. And guess what? That just equal to sa sub 0 plus sa1 times x plus sa2 times x squared plus dot 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 plus san times x to n. And I'm also going to define our zero element. A zero element would be this one. I'm going to call it z of x. Will just equal to 0 plus 0x plus 0x squared plus dot 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 plus 0x to n. Essentially, our zero function or zero vector is just z of x equal to 0. And I'm claiming that this set of objects with these two operations and with the zero element identified is a vector space. Now, before I tell you why it is true, I'm going to ask you to kind of think about it. And some of you might already notice by comparing to the other three that we talk about and the way we define vector addition and scalar multiplication with the other three vector space and how we define the zero element, that you already realize how to argue that this is a vector space. And if you can do that, that's great. If not, take a minute to think, pause the video, take a minute to think about it. And remember, I always tell you guys, sometimes it's not about getting the right answer. Okay, learning about math is learning how to think, how to analyze, how to try to understand what's going on. So the worst thing you can do for yourself is like, oh, I'm not going to think about it, I'm just going to keep watching the video. And that's not going to help you. So take a minute to pause and think about it, okay? And whether you have an answer or don't have an answer, think about it will help you, give you a sense of understanding, better than you just have someone tell you what the answer is. So take a minute to pause and think about it. And then we'll talk about what the answer is. Well, I'll take a sip of water. All right. So now how do I know this is a vector space? So actually it's pretty simple, because if you think about it, the way when we add or multiply or scalar multiply or even define the zero element, we are basically just simply defining the coefficient. So therefore, in this scenario right here, we can think of P of n is a vector space because it is mathematically no different than the same as Rn plus 1. What do I mean by that? Well, imagine the following. Let's say we have the vector space P sub n. So therefore, identify that each element is this. Is a sub 0 plus a1x plus a2x squared plus dot 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 plus a n x to the n. And I'm going to say that this, essentially, from a mathematical standpoint, is the same as the vectors a sub 0, a1, a2, dot dot dot, to a sub n. And this is actually an element in Rn plus 1. If you want a very more specific example, think of it the following. Suppose I have P sub 3, for instance, and I have this very specific function. P of x equal to, let's say, 1 minus 2x plus 7x to the third. Then I can actually interpret this polynomial not as a polynomial, but simply interpret as a vector 1, negative 2, 0, 7. Notice that I need a 0 to hold the place for 0x squared. And that is just a vector in R4, because there are 4 coefficients. And if a vector in R4, or if vectors in R4 would form a vector space, so would this. And also important to pay attention to is that the way we form addition between polynomial functions and scalar multiplication is the same way we define for vector addition and scalar multiplication in Rn. And now, of course, in this case, let's say in P sub 3, we have the 0 element, and we just simply interpret as the vector 0, 0, 0, 0, which obviously is also in R4. Interesting. So therefore, meaning the next time when you have to combine or add or do scalar multiple of polynomials, instead of doing them as polynomials, you can just think of them as vectors in Rn and just do it that way. You'll get the same result. Okay, just with the other things that you have to do is to kind of think back as to how the vector turn into polynomials. Now, if you find that to be surprising, then you'll find that this is probably even more surprising. So this is our last example of vector space. Number 5. Continuous function. Or sometimes referred to as a continuous function space. So let's see square bracket capital X be the set of all functions, all continuous functions, in the form of f mapped from X to R. So in this scenario right here, depending on what X is, we actually will go say that X would have to be in R1 also. So X in this case, something worth writing down for yourself, would define the domain of the function. And we basically talk about all continuous functions from this domain to just the set of real numbers. With X being the domain of f, and it is a subset of R1. So we don't want to deal with multivariable function, and we also don't want to deal with vector value function. So example, if I define this continuous function space C parentheses 0, 1, then that basically defines all continuous function that map from domain 0, 1 to R. And if I want to define, let's say, the continuous function from 0 to infinity, that would be C square bracket 0 to infinity. That would define all continuous function that go from 0 to positive infinity mapped to R. Now, what kind of function will be in this kind of space? Well, technically, any kind of linear function that, any kind of continuous function that you know would exist in it. The only difference is if they exist in, let's say, this space right here, then you just have a restricted domain from 0 to 1. Okay, so if you have a continuous function that go from negative infinity to positive infinity, then those functions will automatically be within these two continuous function space. Like sine and cosine would automatically be in both of these because those two functions are continuous from infinity, negative infinity to positive infinity. So now what we're going to talk about will be the following. So now how would this form a vector space? Well, guess what? The same concept apply. What I'm going to try to do is not to talk about the continuous function, but simply somehow try to think of them as just a list of numbers. So how do we define this vector space? So just like how we're going to do it, we're going to define the objects. So the object will be continuous functions. With domain X. And how do we define the two basic operations? Well, we're going to define the two basic operations the same way you define function operation when you first learn about it in Algebra 2. Suppose I have function f and function g. If I want to add them together, what will happen? Well, you can simply just add them together to form a new function. Example, Suppose I say that function f of x is sine x and function g of x is x squared. Then f of x plus g of x would simply just be this function, which is called f plus g of x, and that would be just sine x plus x squared. There you go. And in some cases, if you can combine the two functions together, combine them together, if they form unlike terms, you just keep them separate. And what happened to scalar multiplication? Suppose I have s times the function f of x. Then what would that be? Well, that just means s times f of x. So same example, if f of x equal to sine x, then 5 times f of x would just be the same as 5f of x, and j is just equal to 5 times sine x. There you go. Now, I know some of you are probably thinking, like, what's the difference? The difference is the following. The difference is that on the left side of the expression, we are supposed to evaluate a function as two separate functions and combine the result. Meaning, let's say I want to evaluate f of 7. F of 7 plus g of 7. So on the left side, I will find out what f of 7 is. On the right side, I will find out what g of 7 is, and then add them together. But on the right side, what we're going to do is we first combine f and g into a new function, and then we plug in 7 on its own. Now, I guess maybe if I give you this example, it will probably help you see better of what does it mean. Imagine of these two functions, and I purposely picked two functions that we can actually combine together so that you can see how they work. So imagine of these two functions here, I have a function f of x equal to 2x and g of x equal to 3x. So now let's say I want to find this. I want to find f of 3 plus g of 3. So option 1, I would do f of 3 plus g of 3, and therefore would be 2 times 3 plus 3 times 3, and therefore becomes 6 plus 9, which is 15. So that's option 1. But I could also do the following. So option 2 would be following. First, I'm going to find what is f of x plus g of x first. And that becomes f plus g of x. And that technically is 2x plus 3x, or f plus g of x is 5x. Then now I realize that f of 3 plus g of 3 is the same thing as f plus g of 3. So that should become 5 times 3, which is 15. So how is these two options different? The order of operation being different. And it's not the first time I said this, and hopefully you have been paying attention, because it's very important to understand that a lot of these things are basically messing with the order operation and telling you that no matter which order you do it, you get the same answer. Very important that you understand this, because it helps you understand how to manipulate your function and expression together. Okay? And same thing, if you think about it, same thing with the scalar multiplication, it's doing the same thing. And in order to define a vector space, I also going to have to define z, the 0 element. So what is our 0 element? Our 0 element will be z of x, which is just a 0 function. Okay? Now, I would like to show you an example of what is a continuous function space is. But it's actually not that easy, because there are infinite number of continuous functions that we can use. So instead, I'm going to kind of ask you to just simply think about why continuous function is a vector space by just going through each of the properties, and try to not write out formal proof, because you will find it very difficult to do, because you won't be able to write out every single possible continuous function that you can come up with, because there are infinite number of them. And there's no pattern to follow. Unlike in the polynomial function, you can write out the polynomial function in a pattern that you can well define, and then you can use the ... to indicate it go on forever. However, if you think of each of the property, you realize that they would all be satisfied based on what we know about continuous function, because sum of any two continuous function has to be continuous, and a scalar multiple of a continuous function will have to be continuous. And if you add two continuous functions together, it really doesn't matter which way you add them, and so on and so forth. All right. So, however, I do want to show you this next thing. And this next thing would allow me to kind of give you a proof to prove some of the continuous function space to be vector space. So the next thing I want to talk to you about is the following. Now, there are a lot of vector spaces that have infinite number of elements in it. The problem is that when we're doing, for what we're doing, sometimes we're not dealing with that infinite number of elements or infinite number of sets of things, objects that we use. So therefore, we can try to reduce what we're looking at into some smaller set of objects. And when we do that, we still want it to kind of maintain the property of a vector space. And when we try to do that, we create, or we are working with something called subspace. Or something called a subspace. So what is a subspace? A vector space can be formed by using a subset, of objects from another vector space with the same basic operation. From another vector space with the same basic operations. So we're not changing the operation to define the vector space, but we're just taking elements from this vector space, but not all the elements, just some smaller set of it to form a new vector space. And by definition, this vector space will have to be quote-unquote smaller in dimension than the vector space. Okay, well, technically speaking, you can, a subset also include every element, so it have to be either equal to the vector space that you get it from or smaller. And because of the fact that it kind of have to more likely have to be smaller, because mathematically no reason to take every element from a vector space to form a subspace, because then you're just forming the same group of same set of objects. So you're very likely you doing it to take out smaller group of objects. So therefore, we call this a subspace. And it might be hard to understand what is a subspace, but once I give you a definition, I'll give you some example, you see why. So unfortunately, this video is almost 30 minutes. So the last thing I want to talk to you about would just be the definition of a subspace. And the nice thing about defining subspaces is the following. Because we're actually taking it from a vector space to begin with, a lot of the properties that we need to prove are already inherent from the vector space. There are basically only three properties that we need to pay attention to because we're taking a subset of elements. So what are these three properties? Number one, we have to make sure that when we take out this subset from another vector space, we have to make sure we take the zero element with us, because otherwise we won't be able to satisfy the zero elements property within the 10 vector space property that we need to satisfy. So we have to make sure we take the zero elements, and also because we're taking a subset of the vector space, we have to make sure that the closure properties still apply, meaning that we don't want to take this subset of object where somehow now, if I take any two elements within this subset and add them together, it now no longer within this subset. So those are the properties we need to pay attention to. So let's go and write this down. Definition. Given a vector space W, let V be a subset of W, then V is a subspace, or properly you should call it sub-vector space, but nobody call that. We just call it subspace, with the understanding that subspace basically meaning a vector space of a smaller vector space of another vector space. So V is a subspace of W with the same two basic properties, basic operations from W if this is true. If V satisfy the following 3 properties. So not 10, because 7 of the properties are already inherent from the fact that we are working from a larger vector space to begin with. So what are these 3 properties? Will be the 3 properties that we talk about. The first would be closure property. So the closure property will be the following. Number 1, if vector u and vector v are in V, then u plus v would have to be in V. That's additive closure. 2, if u is in V, then s times vector u would also be in V. And that's scalar multiplication closure. And 3, the 0 element is still in V. Unfortunately, this video is now over 30 minutes, so I'm going to stop right here. Tomorrow, we're going to talk a little bit more about subspaces, and I will show you some example of some subspaces. And as a matter of fact, we will likely be working with just subspaces from this point on, because sometimes we don't need to have the entire vector space to work with. Like, instead of working with the polynomial to nth degree space, we might look at a subspace of that, which is like polynomial with 3 degrees. Or if we're looking at the matrix space, then instead of looking at the matrix space of all matrices of m by n, we'll look at a matrix C from 3, 2 instead. So things like that. So we'll continue some more tomorrow. Okay, talk to you guys tomorrow. Bye bye.